Thank you very much. Oops. So maybe I should not talk as loud as usual, which for me is kind of a problem. So it's a great pleasure to be here in this distinguished conference for such a great mathematician as Frank. Unfortunately, our acquaintance is kind of only in the late years, and in some sense also the type of mathematics that I'm going to explain today is a bit less related to his work than some other in the conference, and for this reason I will also kind of go slowly at the beginning of the talk, and my main target is actually to give you a good statement of what the main theorems are, but I will try also to give you some ideas, and then at the very end maybe I will try to argue that after all it's still connected to his research in some way. So I will talk about the about results and theorems about the oriented Plateau problem. So oriented plays a very important role. And so roughly speaking, this problem consists on having gamma a fixed contour in the Euclidean space. This is a fixed contour of dimension m-1. And as a fixed contour, you should simply imagine a closed, smooth, embedded surface, which is oriented. And I look for nice and smooth m-dimensional surfaces sigma which bound gamma. So the boundary of sigma in the sense of differential topology is equal to gamma, and minimize the m-dimensional volume of sigma. Okay, so that's the problem that I want to study. It's actually not so fundamental to have a fixed contour. You can imagine that and we're going to replace the Euclidean space with an arbitrary Riemannian manifold, and then you can actually even just think about sigma being a closed surface in some topological class. And in that topological class, given that restriction, you're actually trying to find some minimizer of the area. Okay, in that case, you don't have to care about the boundary. Okay, so now how do I variationally solve this problem in the sense of how do I find a meaningful class of surfaces in which I can actually run the direct methods of the calculus of variations and take an infimizing sequence of such surfaces and find a meaningful limit. Okay, so these are the so-called integral currents, for which I'm going to give you two possible definitions. So one is what like you would intuitively do. So you close the space of nice surfaces in an appropriate topology. And so now for us, the space of nice surfaces are formally finite sums, or if you want, finite unions of nice, smooth pieces of oriented surfaces which have nice boundaries. And these pieces will be denoted in this way. And then I allow actually to make in front of them an integer multiplicity. So I can take like 1, 2, 3, 4 copies of the same surface. Okay? So that's one possibility. And then you're going to close this in an appropriate topology. And the topology is the so-called flat topology. I'm not going to give you a formal definition of the flat topology. Just imagine that there are two reasons why two surfaces might be close. So one reason is that they share a lot of mass together, so they really coincide on a very large portion. Or the other reason is that, so that's why they might be close. Or the other reason why they might be close is because I can, by adding a little bit of extra surface, I can found them as the boundary, or their difference, as the boundary of something which has kind of small area. So it's some sort of L1 distance between surfaces in a geometric sense. And okay, so this class of integral currents is the closure of the nice ones under the assumption that you have a uniform bound on the mass of the consisting objects and on the mass of the consisting boundary. So of course here, when I have somehow something nice and there is kind of no cancellations, the mass is going to be the sum of the masses, or of the volumes, counted with the correct multiplicities. And the boundaries is going to be, the volume of the boundary is going to be the sum of the volume of the boundaries counted with the correct multiplicities. So you think of having these two quantities in control, and you're trying to see what the possible limit of the surfaces are, and then you land on these integral currents. Okay, another possible definition is the following. So I understand an integral current as a linear functional on the space of forms, because what I can actually do on the nice objects, I can compute the integral of the form over the corresponding pieces, and I can sum them up. So now in an integral current, what I'm going to do is, first of all, I'm actually allowing you to take infinitely many of these pieces. And then secondly, I actually allow you to substitute the sigma i's, which were nice pieces of your smooth surface or C1 surface, with closed subsets of the C1 surface. And on this closed subset, I can actually integrate, thinking that I'm using the Lebesgue integral. Okay? So now this is what we call integral rectifiable, if it has a representation like this. And integral amounts to the fact that the boundary of the current has a similar representation. But now, how do I understand actually the boundary of this current? Well, if this is a linear action on the space of differential forms, then what I understand as the boundary acting on it is just the action of the form on the differential of the current on the differential of the form. So by definition, somehow my boundary is given through Stokes' theorem. Okay? So now, here's a fundamental theorem which is due to the Giorgi in codimension 1 and Federer and Fleming in higher codimension. So the theorem tells you that this is the space of integral currents is amenable to solving the Plateau problem, and it's the oriented Plateau problem, via the direct methods of the calculus of variations. So I take an infimizing sequence for that problem, and I land actually onto a minimizer in this space. So that means the space is locally compact, and there's a definition of m-dimensional volume, which is sensible. One possible definition is via, for instance, relaxation. Like, you take all possible approximations with nice smooth objects, and you take the lim-inf of all the possible volumes that you know how to compute over there. Or you can actually take the formal definition over here and just think that the volume of EI is recovered if I maximize this integral over all omega with modulus of omega less or equal than 1. So you can actually define it by duality. There is also another part of this theorem that tells you that nice objects are dense. So that is called the deformation theorem. And in a sense, it tells you that you're not picking up any fake minimizer of that problem by making this extension. So if you find something over here which is a minimizer, you can actually approximate it nicely with smooth objects. OK, so now you know that there is a minimizer through that. And you're wondering about the regularity question. Which is how smooth is how smooth can a minimizer be? Okay, and you immediately have, well, not immediately, so through kind of famous results in the literature in the 70s, you immediately have two very important examples, which are going to set the tone of these talks. So one example is in codimension 1, and it's called the Simon's cone. So, and this is the cone x1 squared plus x2 squared plus x3 squared plus x4 squared equal x5 squared plus x6 squared plus x7 squared plus x8 squared inside R8. So it's a 7-dimensional surface in R8, and you see that it has a singularity at the origin, which is not possible to resolve. It's really a topological singularity. And of course, it's just a cone on S3 times S3. If you intersect this with the unit sphere, you find S3 times S3. So this is in codimension 1. And then there are holomorphic subvarieties. So if you identify R2n with Cn, you can look at any at any holomorphic subvariety of Cn, and it realizes a surface with singularities of real dimension twice the complex dimension. So let me make one basic example, which are going to guide us for some other reason, and it's just the following simple algebraic subvariety. Okay? So this is a 2-dimensional surface in R4 when you understand ZW as 2 complex coordinates. Okay, so there's a famous theorem by Bombieri, De Giorgi, and Giusti, which tells you that example 1 is an absolute minimizer. An absolute minimum of the oriented Plateau problem. So if you cut this surface with the sphere, you get S3 times S3, which is a perfectly smooth submanifold, 6-dimensional submanifold of R8. You're looking for an oriented minimizer of the Plateau problem. You don't find any, because any minimizing sequence is actually converging to this guy over here. So it's kind of, and it's unique. So it's in some sense the unique minimizer in the class of singular surfaces and in the closure of nice surfaces. So something similar actually happens for holomorphic subvariety. So this is a theorem by Federer, which actually relies on the computation of Wirtinger, which tells you that every time that you have an holomorphic subvariety in Cn, you actually have an absolute minimizer of the corresponding real dimension in R2n. So again, I cut this surface with the sphere of radius 1. I find the real analytic curve, which is going around on this S3. And this guy is the unique minimizer in the sense that, well, it's the unique minimizer in the context of integral currents, but also if you take any minimizing sequence in the space of nice objects which bound that curve, you're actually converging to this singular guy. So these singularities are unavoidable. And as you can see, they immediately give us an information. So how smooth can a general minimizer be? Well, a 7-dimensional hypersurfaces cannot be smooth in general. And the 2-dimensional surface in R4, which is area minimizing, cannot be smooth in general. OK, so on the other hand, these examples are matched by the following theorem, which in codimension 1 is the sum of the work of several famous mathematicians. So the Giorgi, Certainly Fleming contributed to it. Almgren, Simons, and Federer. So in the case of hypersurfaces, the dimension, the Hausdorff dimension of the singular set, and I define the singular set as the complement of points where I am regular. And at a point I'm regular if there is a neighborhood where my current can be represented as a smooth embedded submanifold counted possibly with an integer multiplicity, right? As it was somehow the rule for having nice surfaces. So the dimension of the singularity, and I'm talking about the interior singularity, so I'm not discussing what actually happens at the boundary, is at most m minus 7, okay? And m is the dimension of the surface. So this matches that example because in that example the dimension is 7 minus 7, 0, and the singular set is just a single point. Okay, so in the case of higher codimension, this is a theorem by Almgren, and it's a celebrated theorem which is called, in a paper which is called Big Regularity paper, and it says that in general codimension, the dimension of the singular set is at most m minus 2, which again is matched by that example, which is a two-dimensional surface in R4 with a point singularity. Okay, so therefore, actually, I'm going to talk about a kind of further question. So we know that they cannot be regular. We know that we have examples of singularities, and we know that we have a theorem in which the dimension of the singularity matches the dimension of the example. And so the further question that you can ask is which structure can we prove for the singular set? Okay, and you see that there's an obvious example that I can take, and I can actually take just products of these examples times linear spaces. It's another theorem by Federer that if you take products, actually those are minimizers if the factor is a minimizer. If you take a product with a linear subspace, if you take a product of two area minimizers, actually that is not a minimizer. There's a counterexample to that. So, and of course you can see that you can have surfaces, minimizing surfaces where the dimension is matched, but the structure is kind of nice, right? So the surfaces have nice singularities. You don't expect actually this to be the general situation, but maybe you can naively expect that your singular set kind of stratifies. Like, for instance, it would happen for the situation of complex subvarieties. So maybe you have a top singularity of a certain dimension, and then, I don't know, if this were, say, a three-dimensional surface in R5, maybe you have line singularities, and which are done by arcs, and then, the arcs join at some points, and they form maybe a nice tree. Okay, so this is kind of the best theorem that you can possibly hope, and it's somewhat hidden in a paper by the Giorgi about general structure of the singular set of minimizers of variational problem. He has this dream in which he can say, like, it would be really wonderful if we could prove some sort of structure theorem which tells you that the singularities are nicely structured. Okay, so there's some relatively recent bad news on that end. So there's a theorem by Leon Simon in 2021. And the theorem essentially says that there are stable minimal hypersurfaces in Riemannian manifolds, in smooth Riemannian manifolds. whose singular set is a fractal of any assigned dimension alpha for every alpha that you can assign, which is less or equal than m minus 7, which is kind of compatible with this dimension bound. And even though that one is not a minimizer, it's a stable minimal hypersurface, there's a theorem by Schoen and Simon which is telling you that minimal hypersurfaces cannot exceed the bound in this theorem that you have for area minimizers, unless you create something like, unless you're looking at something like minimal surfaces which are kind of crossing. Okay? In fact, said in this way, it's a deep theorem by Vikramasekera, and only rather recent. So you can create stable minimal surfaces which have like codimension 1 singularities by simply taking two nice minimal surfaces and make them self-intersect, which is possible. But as long as you prevent something like that, then you actually go down to the bound that you have over there. And you see that here somehow you're taking an alpha which is less or equal than n minus 7. OK, so that's one theorem. There's another theorem. And this one concerns really minimizers. And this is a theorem by a student of mine. So there exists minimizers in higher codimension who have a singular set with arbitrary dimension as long as this dimension is prescribed to be below the bound that we have from Almgren's theorem. And these are not stable. These are not simply stable. They're really minimizers. They're not local minimizers. They're really absolute minimizers. OK. So there's a little caveat over here that I don't want to actually tell you. But after the talk, if you're interested, I can tell you what the caveat of this example is. I would say it's not really the final answer. But it definitely strongly suggests that you cannot go, that you cannot hope for this the Giorgi dream that you're going to have some structure of the singularities. OK, on the other hand, you can still do something, because, so let me just make the following important remark, which of course is probably obvious to all of you. Once I give you actually a bound on the Hausdorff dimension of the singular set, my singular set might be very far from what is our intuition of a kind of nice set of that particular dimension. So for instance, here I have the bound for m equal 2, that the Hausdorff dimension of the singular set is equal to 0. And maybe I'm imagining that my minimizer has like a few point singularities, maybe countably many. But there are sets, closed sets, with Hausdorff dimension equal to 0 that are uncountable. Okay? So you might actually be very far qualitatively from what you expect from a zero-dimensional set, from kind of a nonist zero-dimensional set. So dimension bound for a set which is equal to 0 does not rule out uncountability for E. OK. There's other. OK, of course, if you are in dimension 0, you can immediately say, well, like, OK, so the nicest kind of sets of dimension 0 that you can imagine are really like sets which consist of finitely many points. And then you can go a little bit further and maybe say, like, OK, maybe I can swallow something which is like the union of countably many points as still kind of zero-dimensional. But having accountability is kind of a quite big jump from that. So there's a definition which in some sense mimics the difference between being countable and having dimension 0 in general dimension, and this is rectifiability. So E is rectifiable, or is k-dimensional rectifiable, if I can cover hk almost all of E with countably many C1 surfaces of dimension k. Okay, so if I go there, then there's a beautiful theorem by Leon-Simon in the 90s that actually tells you that for hypersurfaces, minimizers have a rectifiable singular set. So the singular set of minimizing hypersurfaces is m-7 rectifiable. And so if you confront with this example over here, it's kind of telling you that that seems pretty much the best you can do. Unless you believe that somehow this stability condition is actually the one which is the obstacle between having more structure and having the possibility of fractal subsets. And in fact, this one, as you can see from the definition, doesn't come with the information that the set has finite volume, finite m-7 dimensional volume. But there's a beautiful theorem by Neighbor and Valtorta and that's, I believe, in 2018, which actually says, in fact, this singular set has finite m-7 dimensional measure. At least as long as I stay away from the boundary. No? But in fact, there's a theorem by Hard and Simon that tells you that the surface is completely smooth at the boundary. So singularities are not clustering towards that. So it really has finite m-7 dimensional measure. And this theorem over here comes with a little added bonus, which I will explain you in like 5 minutes. Because before coming to that, I just want to present finally the main result of the talk. So the counterpart of this on higher codimension minimizer has been open since the work of Almgren, which dates back to the 1980. And that's what we have been able to resolve just recently. OK, so this is the main theorem. And that's a joint work of myself, Paul Minter, and Anna Skorobogatova. So that's one paper. But the proof is actually spread through 3 papers. And the other 2 are joint works by Anna and myself. OK, so altogether, these 3 papers, they actually prove that the singular set is m-2 rectifiable in general codimension. And it has the same added bonus that the theorem by Leon-Simon has, which I'm going to explain you again in a few minutes. So it's a complete counterpart of Leon's theorem in the general case, but it doesn't have this feature. we're not able to actually say that the m-2 dimensional volume of the singular set is finite. And in higher codimensions, the situation is bad in the sense that the singular set might even cluster towards the boundary, but it's really a problem even just in the interior. I can just tell you, I cannot tell you that away from the boundary, my set has finite measure. I have some countable decomposition in pieces which have finite measure, which is an obvious outcome of the definition, but which is also something that you can work through the proof. The proof gives you a construction of how to sort of identify these finitely many pieces, these infinitely many pieces. So they are countably many, but they could actually cluster inside. Okay, so actually, so this is the fun of mathematics. Even though this theorem took like 40 years to be proven, at the same time, this has been proved by Krummel and Vikramasekera. And so the proof is also split into 3 papers. The proof is also following a strategy which is very close to our strategy. Pieces of the strategy are implemented in a very different way, though. And if you want to be picky, so these 3 papers, 2 of them appeared 3 days before our 3. And 1 of them is announced in these 2 papers, and it still has to appear. I'm going to explain you what is a little bit about the general strategy over here, which is essentially the general strategy that they have. And that they have come up with independently from us. So we were completely unaware that they were doing this, except that at a certain point on a weekend, we saw the 2 papers appearing and announcing the 3rd one. And that's when we were essentially like correcting the last couple of sections of this paper over here. Okay? So for us, interesting enough, for us, like, you know, the chronological order is really like, you know, this paper here, this paper there, and that one. And for them, the first starting point of the proof is kind of mirrored by what we do in this paper 1. But the second that they published is what we actually did last. And what they announced is kind of the middle piece. OK, so first of all, why is it complicated to actually prove this theorem? It was actually complicated by, I mean, for Almgren to prove even just the dimension on the dimension bound on the singular set. Whereas I would sort of advocate that the theorem which gives you the Giorgi, Fleming, Almgren, Simons, Federer result is less complicated and much better understood in the literature. So, well, first of all, let me tell you that there's something which is called monotonicity formula. So the monotonicity formula, which is a very basic, simple computation, tells you the following fact. So if you have an area minimizer, or if you have in general a critical point of the area functional, so if you look at the mass ratio, so if you look at the m-dimensional volume of sigma intersected with a ball of radius p, and so you divide by the volume of an m-dimensional disk of the same radius, and normalize it by a number which just tells you that this one is really the volume of the disk, right? So this is just the scaling. This is just the exact computation of the volume. So this function of r is non-decreasing. Well, as long as this ball stays away from the boundary, okay? So this is one information of the monotonicity formula, but it comes with an extra information, and it is constant if and only if sigma is a cone. So this is actually valid in high generality, even for very kind of general, generalized minimum surfaces. And it tells you something very interesting. If you look at the point and kind of zoom in and rescale, right? So this, when you make an homotopy, somehow this is exactly what becomes, say, the volume of the rescaled surface on the ball of radius 1. because this is exactly the factor, the magnification factor in the volume which is given by the homotity. So that quantity stays bounded, which means that I can use my compactness theorem to extract limit up to subsequences. But not only it stays bounded, it converges to something. And if you have a little bit of improved convergence, so if the volume of these objects converge to the volume of the final object, which is a case, for instance, for minimizers, then the final object you land on actually has a constant ratio, and actually it's a cone, which is a very, very beautiful information because it tells you that in terms of dimension complexity, your kind of limit of the zoom, so your rescaling, when you're zooming in on the surface, you actually lost one dimension. So for instance, if you were a two-dimensional minima surface, now you're discussing a two-dimensional minima cone, and the cross-section of the cone is a one-dimensional curve. Okay? So one thing that you might hope of is to classify all possible such objects, so all possible cones. And of course, if you were in the situation in which you actually have a smooth point, the cone that you're seeing when you're actually making this rescaling is just a flat plane. And in some sense, the possibility that there are cones which are not flat planes, it tells you how big the singular set can be if all that you have are singular points where the rescalings are converging to a cone which is non-flat. Okay? So there's a big difference between codimension 1 and higher codimension. So codimension 1 is so much easier because there's an epsilon regularity theorem which dates back to the Giorgi's seminal work, which tells you that if you're sufficiently close to a flat plane in the weak topology, that's very important because that's the topology which is given by the convergence, then you're actually smooth. Say, at half the scale. And so this epsilon is just a quantification of how close you actually have to be. Now, this tells you that when you're actually looking at the singular set, all you have to care about are points where all the rescalings, I didn't tell you that the rescaling is unique, because I just have a compactness, so it might depend on the sequence that I'm taking. I'm actually interested at the points in which all the rescalings are converging to a singular cone. For instance, as soon as you prove me that there are no singular cones, I can't have singular points. And that's how you get actually to that dimension bound, to that n-7, right? But in higher codimension, this is false. And I already gave you an example. Right? So if I take this complex subvariety, well, OK, so the whole problem in the singularity is on the fact that when I'm taking square root of complex numbers, I have two values and they're branching out, right? But if I ignore that, and if I think that that one is actually a very high perturbation of this w squared, because after all, I have w to the power 2023 divided by 2. It's really tiny, tiny, tiny perturbation. So my surface really looks like this way, right? So I have something quadratic, and then on top of it, something, yeah, if I draw it green, certainly you're not going to see it. So let me draw it yellow. So something which is really, really a tiny perturbation of it. And as I'm zooming into the singularity, pretty much I pick up the quadratic behavior, and these two branches, they're actually going to collapse. So I'm not going to see them in the limit, right? So this is completely false over here, which tells you that if I want to understand what type of singularities I get in higher codimension, I need to understand this type of picture, which you can see it's a singularity which happens at a very, very high order. So the singularity that you have over here has homogeneity 1 in a sense. I can already capture it even if I have some sort of Lipschitz bound, right? So the singularity that I have over here, it's actually with some order, and I don't know what is the order of what is the degree of the singularity, right? So it's just some number, which, yeah, it might be 2023 divided by 2, which is awfully high, but it might actually be 1,000,000,001 divided by 2, which is even higher. OK, so now what can I do, though? So in codimension 1, equipped with this, there is something which is called Federer's reduction argument. which is essentially playing on the following extra information that is still coming from the monotonicity formula. So if I have, say, a cone with some singularity over here, and I see another cone with a similar singularity over here, and overall, at this scale, my surface is not too far from being a cone. Actually, the only way this could possibly happen is that the cone splits off a line. So if I see a picture like this at this point, and a picture like this at the nearby point, and the 2 points are very, very close, so close that I start actually seeing a cone already at a slightly larger, scale, the only possibility this could possibly happen is if your cone actually has the structure of a product of a core cone, which has an isolated singularity, times a line. Okay? So this Federer reduction argument tells you that under some assumptions, essentially, if I am close to a cone which has a product structure, my singular set has the tendency to cluster around the spine of this cone, somehow around the factor. So it gives you some sort of linear approximation for your singular set. So your singular set at a sufficiently small scale is going to be kind of on a slab of this kind. That's actually the way you can efficiently kind of bound the dimension, because once you have an information like this, you can start covering your singular set, which is the yellow line, by a number of balls which is kind of proportional to the dimensionality which is given by the spine. But this is a very soft argument, and when you're actually performing the soft argument, you're losing a little bit of a power on the radius. So that's why you're actually only able to bound the dimension of the singular set, but you're not going to be able to do rectifiability. If you want to do rectifiability, you can actually have to do much more. So what is the much more that you actually want to do if you have rectifiability, where you need a theorem which is kind of comparing how much, say, for instance, if you have two situations like this, at two different scales or nearby, how much is the possible tilt which you might see between two such things. And in some sense, the approach which is taken by Leon over here would be the following. So in a dream scenario, I would like to have a theorem which is telling me the following. So the theorem is telling me that actually the tangent cone that I see over there, so when I make this rescaling argument, is unique, is independent of the scale that I'm taking. And not only it's unique, but it has actually a nice convergence rate. At the point that if I am at two kind of nearby points, and I see a situation which is almost like this, and a situation which is almost like that, because I have a nice convergence rate on this point and a nice convergence rate at that point, I will actually have not only the uniqueness of the tangent cone, but I will also know that the the tangent to my set, to my singular set over here, and the tangent to my set at the singular set over there will have an estimate on the tilt, which somehow results into not only a proof of rectifiability, but the proof actually that your singular set arranges in a nice graph, which is the graph of a surface, which is, sorry, the graph of a function, which is also C1, because I will also have an estimate on the tilt. Okay? So let me call this ideal scenario number 1. Unfortunately, it's still open. So we don't know that there is uniqueness of the tangent cones. We don't know that there is a nice decay to the cone. And actually, there are quite nasty examples by Leon himself that there might be cones to which the rate of decay is logarithmic. I mean, the ideal scenario would really be that the rate of decay to these cones is actually a power law, which would result into a C1 alpha estimate or on Hölder estimates on the continuity of the tangents. And we're very far from that. I mean, it can actually even decay logarithmically. OK, so the beauty of this theorem over here, though, is that you don't need to be so sophisticated. So they had a beautiful realization, which essentially just tells you the following. So to prove rectifiability, you have to prove a quantitative L2 version of these controls of the tilt, which is per se already a beautiful achievement in geometric measure theory. And there was a parallel paper by Atsam and Tolsa in which they characterize rectifiability in this way. But the power of this theorem is that the monotonicity formula itself, with the remainder, if you study it carefully, precisely has the structure which gives you this kind of tight characterization of rectifiable sets. So essentially, it reduces a hard PDE problem in the approach of Leon-Simon to a hard GMT problem. So it has taken away a lot of the decay PDE estimates that you have over here to prove this theorem, which he can, even though the ideal scenario is false. And it has reduced to something quite powerful, which is like looking at the structure of the monotonicity formula that you have and proving certain estimates in there, and then just from them actually extract rectifiability. OK. So, but let me get to this theorem. So if you want to understand that theorem, let me see. OK, this is a bad idea. So maybe let me start over there. Or maybe there's another. Yeah. So actually, I can kick this out. And there is another one. Oops. Thank you. OK, if you want to prove that theorem, and that is the reason why even Almgren's dimension bound is so complicated. So if you want to prove that theorem in higher codimension, there is another layer that you have to understand, because remember our example. My singularity is a high order perturbation of something which is actually smooth. So I have a second ideal scenario, which is even more problematic than the ideal scenario number 1. The ideal scenario is that, well, I have some singularities in which I actually never see a flat tangent cone. And those are dealt with by this neighbor-Valtorta theory.
You want to take away the factor of the power 2 on the left?
Oh, yeah. Well, I could keep it, actually. But yeah, yes. That was my initial intention. Right. So I can sort of avoid discussing the places where I see tangent cones which are singular. And I can just restrict myself at seeing like the nasty singularities. On the other hand, those are like the responsible for the 2,000 pages proof of Almgren. So now over here, what I would like to do is, in the ideal scenario 2, I would like to know that, well, first of all, I know there is a flat tangent cone. I would like, really love to have that unique. Once I know that that one is unique, I would like to understand this kind of further expansion, so kind of modding out the regular part, and then being able to capture the real singular behavior of the surface, and hence prove rectifiability. Okay? So I would need uniqueness of tangent cone. Excellent decay rates. And an algorithm to find first a smooth interpolation of the singularities. Or actually not a smooth interpolation, but the best smooth approximations. OK, so fortunately, in a series of works which I started some 15 years ago, so we have an understanding of Almgren's theory which is much more efficient than his original big regularity paper. And this is through a series of work by myself and Emanuele Spadaro. Now, if you look at the constructions that we have for this thing over here, which is what Almgren calls center manifold, and which is like the biggest analytical problem in his proof, and which in our proof is kind of, I think, better understood, at least the proof is kind of a factor 10 shorter. What you actually realize is that to have the uniqueness of the tangent, I mean, like once you have the uniqueness of the tangent cones, you actually need a decay rate which is almost quadratic to the tangent cone. And then you will be able to extract this part over here, the center manifold, in a way which is homogeneous in all the singularities. And now you have this kind of nice, smooth interpolating surface. And over this nice, smooth interpolating surface, you can use the first part of his theory, which is the theory of multi-valued approximations for area minimizing currents. Because you see that even though I'm very, very flat compared to W squared, I still need two values to kind of understand what my current is doing on top of it. And then there is something which he invented, which is called frequency function, which is a way of computing this homogeneity over here. So the homogeneity of the singular model. Once you have a way of computing this, there is, with this monotonicity formula that he has, with this frequency function, something which is parallel to the monotonicity formula upstairs, and which allows you to actually use the Federer's reduction argument. Okay? So now, half of this paper, of paper 2, plus a previous work of myself, Marchese, Spadaro, and Valtorta, tells you that this framework adapts in that case. So remember over there that the reason why it works is because we have a monotonicity formula, and the monotonicity formula has certain structural properties. And what we actually prove in this paper is that for harmonic multivalued functions, which are some sort of linearization of what you want to do in this situation, that framework applies. So you have the rectifiability as a consequence. And then what we do in the first half of this paper, we adapt and we carry the nonlinear estimates to actually show that in this ideal scenario too, we can prove that the singularities are rectifiable. Now, unfortunately, the ideal scenario 2 is wrong as much as it is wrong the ideal scenario 1 for even more reasons. And that's the reason why this one is only half of the proof. So first of all, you don't have uniqueness of the tangent cones. Or better said, we don't know if there is uniqueness of tangent cones. Maybe there is. But certainly, having excellent decay rates to it is not true. There are just examples in which the decay rate are polynomial, but just a tiny bit polynomial, so they're certainly very far from being quadratic. I mean, polynomial now here, I mean power law, right? OK, so the second part of paper 2 actually deals with the issue that we might not have decay rates. But then there's still the problem that we might not have uniqueness of the tangent cones. I mean, that's where it actually gets much, much harder. So what actually paper 1 does is the following thing, which at first looks miraculous. So maybe there's no uniqueness of the tangent cones. Maybe there is uniqueness of the tangent cones, and I don't have good decay rates. On the other hand, we can tell you what this power should be at the point, independently of the radius. So I don't have a unique way of extracting this kind of smooth part. Maybe I can't extract the smooth part because maybe I'm close to a tangent cone which is not flat. But when I am close to a tangent cone which is flat, I can find the smooth part, and I can find an approximation which is kind of roughly homogeneous with a certain order. And I can tell you that the degree of homogeneity is independent of the scale at which you are. It depends only on the point. So that is what is done in paper 1. Now, what do we do in paper 3? Well, in paper 3, we just identify, so this number can be 1 or higher. So this homogeneity can be 1 or 1 plus alpha somehow. And as long as it is 1 plus alpha, we are in this situation. So we can deal with the second paper, the second part of the second paper. The really problematic points are points in which the homogeneity might be actually be 1 of that approximation. And this one, which is the hardest work, actually shows you that those points have Hausdorff n-2 dimensional measure 0. So we don't know how to analyze them, but they are a null set in the n-2 dimensional volume. And so what was the added bonus that actually comes with this theorem over here? And the added bonus that comes with this theorem over here? Well, at almost all points, I can tell you that there is a unique tangent cone. So either there is a flat tangent cone, and the set of points where I might have non-uniqueness is actually a set of measure 0, or I can actually, or I don't see any flat tangent points, I can apply the neighbor-Valtorta theorem, and once I have the, and I mean the neighbor-Valtorta theorem actually together with the analysis that we perform over here, it gives you the uniqueness of the tangent cone at that point. Okay, and with that, I'm finished. Thank you.
Maybe we have time for a couple of quick questions.
Are there results in the Lorentzian signature case, and in particular for membranes 2,1 in 10,1?
Not that I know of. So all of this is strongly using the fact that the problem is elliptic. So I know of works in which people produce kind of smooth objects, but I don't know of works in which there is a framework like the one I actually described when I'm not in the elliptic case.
Because the big problem of membrane theory is that apparently it develops fingers. I mean, which look like
your metric is Lorentz, but you are still looking at the space like hypersurface. So it should still be elliptic.
Okay, let me think about that. It's still an elliptic problem. Then it's something that we should actually look at. But okay, I'm really unfamiliar with it to be able to say.
Camillo. So this results about rectifiability is dealing with sort of the highest allowed dimension of singularities. Yeah. So okay, the dream of having stratification is not realized, but if you restrict yourself to, let's say, holomorphic or maybe pseudo-holomorphic varieties,
you do have them. You do. Okay, so on holomorphic, of course, you have.
What about the pseudo?
No, pseudo-holomorphic, you're running in the same problem. But let me come to, like, the connection to his research, which I promised you. Okay, so let me substitute the Giorgi's dream with my dream. Okay. So, actually, why is it so bloody hard to prove that that stuff is rectifiable? It's because these singularities are unstable. They're highly unstable. I mean, like, you perturb them. You look, for instance, at the data which gives you the Simon's cone, the S3 times S3. You just perturb a tiny bit, and poof, the point singularity has disappeared. So a possible dream is the following. There's a type of singularities which are the ones which are creating these problems. And in particular, like for higher codimension, all of these holomorphic singularities are of that type, actually, because, like, you can just resolve them even in the holomorphic category. Okay, they're giving you a very hard time, but actually, by a generic perturbation, I can make them disappear. Then maybe what's left, which are kind of the stable singularities, they do have a structure. That is a possibility. And the possibility is somewhat confirmed by some results of this PhD student of mine that I raised from the backboard, from Genoa Liu. For instance, he has some situations in which codimension 3 singularities are stable, and they kind of arrange themselves in a nice way. But that's, I think, the best you can possibly dream. Of course, the other thing is, like, you might believe that all of these examples in which you have fractality, it's because of the smooth ambient Riemannian manifolds. So maybe if you are in the Euclidean space, or if you are real analytic, there's no such problem. Okay, so maybe for real analytic kind of ambience, you have a stratification and nice singularities. But I would be a very kind of, unsatisfied. I mean, it would be a fantastic theorem, no doubt about that, but somewhat unsatisfied, because, there's lots of situations in which, You don't want to restrict to something which is real analytic, for instance, because you want to cut and paste a manifold or do operations like that, and that would be all forbidden. And if I really had to bet a little amount of money, I would actually bet on the fact that it's not really the real analyticity the problem, but it's really the fact that the singularities are unstable.
Okay, so if there are no more questions, I guess we should thank the speaker again.